Okay, so to solve this problem, let's first calculate the rate of this reaction that we would expect. So first of all, what do we know? Well, we know that this reaction is elementary, which is really important. So because this reaction is elementary, we know its orders with respect to each of the reactants. We know that its order with respect to x is 1, because the coefficient of x is 1 here. And we know that with respect to y, it's 2. So how do we calculate the rate? Well, we have a basis here. We know that the rate is 0.001 molarity per hour in these conditions. So when we increase x by a factor of 10, since its order is 1 with respect to x, that means that we're going to increase the rate by a factor of 10. When we increase it by a factor of 5 on y, well, y is order 2. The reaction is order 2 with respect to y. And so we're going to multiply it by 5 squared, or 25. So we're multiplying this by 10 and then by 25. And so our rate is going to be 0.25 molarity per hour. So if we extrapolate this over 4 hours, right, we would expect to see a decrease of 1 molarity in the concentration of X. So we'd expect it to go to 9 molarity. So we might be led to think that the final molarity will actually be exactly 9, but this actually isn't right. And that's because the rate is dependent on the concentration of the reactants. And as the reaction happens, the concentration of both reactants, of X and Y, go down, right, because they get used up. And so the reaction actually slows over time. The rate goes down a bit. So over the course of these 4 hours, the rate is actually going to decrease, and so the average rate will be will be at least to some extent lower than this 0.25 molarity per hour rate, because that's only the rate for the first small amount of time. So therefore, since the rate is in actuality a bit lower than this across the 4 hours, we consume a bit less than 1 molarity, and so we actually are going to be slightly more than 9 molar on X, because we don't quite use up a whole molarity.